Okay, welcome back. Right, what I'm going to do, Sarah gave you a background introduction to fingerprints and our perspective of looking at this. And the idea behind that was to give some sort of real overview of the environment that fingerprints is in at this particular time. And then you can get some appreciation of why so many people are saying, we need to think about probability, we can use probability. But in order to understand that, you need to understand a little bit about probability. So what I'm going to do now in this presentation is give you an overview of some basic probability concepts. I'm going to focus only on those ideas that you need to know to understand the software that we're going to use later on today and tomorrow. So I'm not going to teach you how to use probability. I'm not going to teach you everything there is to know about probability. I'm just going to give you all that you need to understand. Okay? And that's quite an important concept for you to take away from this presentation and other work that we do today. And I stressed it in the introduction. This is not a training course. This is about understanding the ideas behind the use of probability in fingerprints. It's not necessarily about giving you any skills that you can use, particularly in a court of law. Although later on, in one of the presentations, I will indicate where you might want to use that information. Okay, so what is probability? Well, first of all, let's look at forensic science. What do we do in forensic science? For any forensic science investigation, what we're dealing with is uncertainty. Now, naturally enough, as I talk about this, everyone in this room, well, the fingerprint people in this room are going to think about fingerprints. I guess there's a few tire track and tool mark examiners. They'll start thinking and putting in terms of those. But if you think of any of the ideas of forensic science, the fibers left at a crime scene, did they come from a particular coat worn by the suspect? Was the paint on the jacket, did that come from the crime scene? The hair left by the individual at the crime scene, did it come from your particular suspect? These are all uncertain events. And forensic science is about trying to determine how likely was it that that particular thing took place? How likely was it that those traces were left behind? So what we need in forensic science is a way of assessing the likelihood of a specific event. And that's really what forensic science is all about. But given the way that our assessment is being used, given the fact that we are dealing with people's liberty, or worse, if there's capital punishment, obviously our evidence could be significant to, well, quite significant to that individual's future. We need to have a reliable system of doing this. We can't have forensic science which is based purely on intuition. And there are a number of examples you can look at around the world in different legal systems where this idea of, I am an expert, I've got 40 years experience doing this, I have a degree and I have this and I have that, being believed when they say, well, actually black is white. And you can't have that type of approach, that type of all about the expert. And thinking back to what Sarah was saying about this is not all about the expert. Okay, so what we need is a way. Is there a way we can actually look at assessing evidence, working out the likelihood that a specific event took place that is more than just my intuition? Well, either luckily or unluckily, depending on your perspective at this particular moment in time, there is. The science of statistics, it says there, it's not really a science. Statistics is a branch of mathematics. And that can be of assistance to us. In fact, we can look at what we actually do now in fingerprints, and I'll demonstrate this later on, and see that you're actually working probabilistically now. You just don't think of it that way. But statistics has two different parts to it. The first part is what we understand by statistics. These are the counts. The means, the averages, the standard deviations. It's dealing with large sets of numbers. It's the stuff you see printed out every day about unemployment statistics or anything. That type of statistics we're very common with. Well, luckily, that's not the type of statistics we're going to talk about today. That's not really what we're interested in. The second branch of statistics deals with uncertainty. It's about working out the likelihood or the unlikelihood of a particular event. And it's that idea of uncertainty that we're interested in. Okay, so probability. like I say, we're going to separate that from statistics, and we'll always talk about probability. So the first thing there is you will see in lots of the work that's being published at the moment, lots of discussions. If you go to conferences, they will talk about fingerprint statistics. From my perspective, that's the wrong use of the word. That's misleading. We're talking about probabilities. And we can define two types of probability, and there's no need really to capture this. This is just to give an idea of how probability works. You can talk about this aleatory form of probability where you deduce the observation from a system. It's an ideal probability. Or you can talk about an inductive process when you're talking about observation of a system having real probabilities. Okay. And anyone who reads Sherlock Holmes will be aware of deduction. Really, deduction is talking about taking a specific event and working out to, sorry, I'll start again. It's taking a general event and working back to a specific. So it's looking at a set of different things that take place and saying, because that happens, then this is most likely to happen. Whereas inductive is working in the opposite direction, taking one specific event and then saying, well, because that's happened, then everything else is going to happen in the same way because I've got this one event. Obviously, that's a little bit more dangerous. Good news is you won't have to remember those terms or think about that. Again, it will pop up once more in this presentation, but it's not something you need to rely on, which is just as well as I sort of got it wrong to start off with. Okay, so probability is a branch of mathematics, and that means, unfortunately, we're going to need to use some mathematical language. Anyone really good at mathematics in the room? Good. That's just what I wanted to see. I'm not. I'm not good at mathematics, and so I've written this very much in a way that is approachable for somebody who doesn't know any maths. But mathematical language is exactly what we say it is. It's a language. Sorry to the lady in the back there, but maths is really, mathematicians said, well, hey, let's invent a language to write everything down, then nobody will understand us and we'll look really smart. It's a bit like IT guys. You know, if your computer goes wrong, you phone the IT guy and says, my computer's not working, and he tells you to reboot it. He doesn't say switch it off and turn it on again. He says, oh, I've got to reboot that. Because it makes him sound like, oh, he knows. Okay? So maths is really a language, and just like any language, if you learn the language, it makes a bit more sense. Okay? And the sort of thing with probability, we're not dealing with manipulation of numbers. So we're not dealing with, you know, simultaneous equations and long division and multiplication. We don't have to do a lot of that complicated number juggling in probability. Okay, but I'll keep the ideas really, really simple, and part of that is because, like I say, I'm not a mathematician. I don't have any formal high education qualifications in maths. I have my basic, in your terms, high school certificate, if that's the right term. Okay, so what is probability? Well, we're going to go through some very simple ideas, and out of those simple ideas, I will draw some of the concepts that you need to understand. So we can talk about some laws of probability. Well, they're not really laws in the understanding that we have. They're not like natural laws. They are concepts. It's in, I put in quotation marks there because depending on which book you read, you will get different interpretations of these laws. But this is probably the simplest one. First of all, probability. In parentheses there, I put PR, mathematical symbol for probability. Again, you'll see some variations. But that's all PR means. And it can take any value between 0 and 1. Well, why between 0 and 1? Simple reason, somebody decided between 0 and 1. There's no underlying reason why it's between 0 and 1, or I guess whoever decided thinks there's an underlying reason. It could have been 16 and 32, 185 and 12. 0 and 1 is what they decided. So when you have a probability of 1, you have absolute certainty. It means that that event is going to take place every time. So first question for you, after break, I hope you're all sort of geared up and ready. What things in life are certain? Death and taxes. Okay, anything else? I did have one gentleman who said death, taxes, and his wife nagging. Which is also bizarrely uncertainty as well, but there are. Yeah, death and taxes. Well, are taxes certain? It's just possible that our governments might suddenly decide that they're going to give us a free holiday and not charge us any tax for a month. It's highly, highly unlikely, but it's not impossible. It's not something that could not ever happen. So it's not actually a total certainty that we are going to get taxed. Death's a little bit more difficult. Certainly when you die is an uncertainty. Certainty you're going to die? Well, I guess it is a certainty you're going to die. You know, hopefully sometime for me and sometime in the next 5 minutes. But there is this thing, well, you don't know when you're going to die. And if you look at medical science, if I was to go back 300 or 400 years and say, well, you know, is it certain you're going to die? Yeah, I'm going to die by the time I'm 30. So it's not so, but it's a difficult one to sort of explain away from. One of the other ones we get is the sun's going to come up tomorrow is a certainty. Well, that's easy to deal with. We know the sun will go supernova at some point. Again, hopefully within the next 5 minutes. That's going to happen. We just don't know when it's going to happen. When you have naught, probability of naught or zero, basically it's impossible. It's saying that that could never happen. So those are ones that are easy to think of. I am not going to win the lottery. And I know I'm not going to win the lottery because I don't buy a ticket. Again, this gentleman said that it's impossible his wife would ever stop nagging. So that's another one. And there's lots of things you can think about as being impossibilities. Okay. Now, the thing with probabilities are also odds. And you can relate them back to odds. So does anybody bet on horses or football or dogs? You're used to the sort of idea of 1 in 10, 1 in 1,000, these odds. That's all a probability is. An odd is calculating the certainty or the uncertainty of a particular event on which you're going to place I think an extortionate sum of money. And if you can relate those odds, 1 in 10, you can convert those into decimals and you can see how they fit between 0 and 1. So this is just another way of writing them. Okay, we have a second law of probability, and this says the sum probabilities of mutually exclusive events equals 1. So what do we mean by that? Well, a mutually exclusive event means that either the event can take place or another event can take place, but neither of them simultaneously. So if you think about event A and event B, if A happens, B cannot happen, and if B happens, A cannot happen. What is certain is that either A or B will happen. So you can see that A and B, the probability of A and B happening is 1. So therefore, the sum of the probabilities of A and for B has to sum up to 1. And that will come up a little later on when we go through some examples. Now, those are the first two laws. And we'll go back to this idea of real probabilities. The thing with real probabilities is they're induced by observation. A realist probability talks about frequencies. You might hear the word frequentist approach to probability. And that's dealing with large numbers of outcomes, large amounts of data, extrapolating that data to work out the likelihood of something happening. Okay. So let's think of a simple example. What is the probability of rolling a 6 with one roll of a die? So you're going to roll one die once. What's the probability of you rolling a 6? 1 in 6. Fantastic. And who? Lady in the back's obviously a mathematician. Strange enough, kept quiet. Everyone else came out with. Everybody else came out with exact. Yeah, it's 1 in 6. Okay. Very simple. See, you told me you couldn't do probabilities. So how did you calculate that? You considered the number of events being considered, which was 1 event, getting 1 6, and the number of possible events was 6, because you could only have 6 events. So it's 1 in 6. Very, very simple. That's all you need to know about probability. But there's some things in there. First of all, we've made an assumption. Anybody got any ideas what assumptions we've made?
Fair die.
Exactly right. You got a fair die. You did the course before. Then you got a fair die. What do we mean by a fair die? Yeah, different number on each side. The sides aren't weighted. In other words, it's the sort of die you don't get in Las Vegas. Okay? It's the one that's got an equal chance of each number coming up. And that's what a fair die is. Okay? But that's unlikely in the real world. Why is that unlikely in the real world? If you think about a die, it's got 6 dots of ink on one side and 1 dot of ink on the other. By any definition, it has to be weighted slightly on one side. Admittedly, it's such a minute change in weight that it's not going to affect the rolling of the die. And obviously die manufacturers go to a lot of trouble to make sure that they roll equally. But it's an assumption. Okay? And because we made that assumption, what we've created is a model. Another word you will hear used and misused when people talk about probability. A model is a construction of reality in mathematical terms. What you've done is you've looked at the die, you've made an assumption that it's fair, and in that you've created a model which you can then use to say, well, my expectation is the likelihood of rolling a die is going to be 1 in 6. So this word model, in a mathematical sense, means this construction of reality. It's not an exact picture of reality, but if it's a good model, then it will be very, 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 very close to real. Okay. So we made those assumptions, we created our model, but of course, the other thing with assumptions is, and you have to point this out, if you make any assumptions that are wrong, your model's going to be wrong, your outcome is going to be wrong. Okay? So if I was to think that the outcome of rolling 1 6-sided dice was going to be 7, I think my model is not going to work. Hopefully. Okay? Now, the one thing about the software that you'll see demonstrated later on, and in fact, all of the current versions of Fingerprint probability software, because the software you're using is not the only version that's being developed, they don't make any assumptions. So they get round this by a little trickery to get around the sides and the way they're constructed, but they don't have to make any assumptions. Sarah mentioned some of the probability work that's been done in the past, which you can read in various books and stuff. A lot of them make assumptions. And that's the danger, because if you make an assumption, the assumption's wrong, then your probabilities will end up being incorrect. So, and I will try. I now have 2 fair dice. What's the likelihood of me throwing a 6 on both fair dice? And it doesn't matter if I throw 1 dice twice to get 2 6s, or 2 dice one after the other, or 2 dice together. What's the probability of me getting 2 6s from those single rolls? Any takers? 1 in 36? I'm just looking for the mathematician at the back to nod ahead just before. Yeah, 1 in 36. Okay, how do we calculate that one? Well, somebody can help me out here. I can't remember how I did. Okay. And did we make any assumptions? Just think about that for a second. Well, how do we calculate it? We just multiplied the odds of each event together. But in order to do that, we had to make an assumption. Okay. Anybody? Well, I just told you, actually. So we made an assumption that they were independent. We said that those 2 events were independent. If I roll 1 die and I get a 6, it does not affect the roll of the second die. Again, if you had a dice, so you rolled 1 and got 6, and then rolled a second die and got 6, that would be a set of dice you want to take to Las Vegas. But they're not. They're independent. They do not influence each other. Okay? If they did, if they were dependent events, you could still work out a likelihood, but it would be far more complex. So, even simpler, how about tossing a coin? Okay, likelihood, and I'm going to tell you this one because I think you can all work this one out. The likelihood of tossing a head with 1 coin is 1 in 2, or 0.5, or 50%, or however you want to articulate that. 50-50. So, again, we've assumed that coin is fair. Everyone understand what I mean by that? We've assumed that it actually does have a head and a tail. It doesn't have 2 heads. We've assumed that the head hasn't got a large lump of lead attached to it, so it also comes up tail first. Okay. And again, we've created a model because we've said, if it's a fair coin, this is what the likelihood is going to be based on the number of outcomes. Now, the question is, how accurate are models? And this is a very, very simple example, and I appreciate it's very simple. It's meant to be very simple. But how accurate is that model for tossing a coin? If I was to pass a coin out to you all now and get you to toss it, what's the likelihood that 50% of you are going to toss tails and 50% of you are going to get heads? If I ask you to toss it 10 times, what's the likelihood that each of you are going to get 5 heads and 5 tails? Would you expect that to happen? No, because the model says this is going to happen, but the bit that we didn't put there was the long run. The point about models is that you only expect to see an answer which is close to the result in the long run. So with a coin, we're quite lucky because we have 3 rather sad individuals who spent their time tossing coins. All of them are mathematicians. Commentator Buffon, well, I normally say he was French, but I probably didn't want to say that. He was French, which probably does explain why he tossed this coin for 4,000 times. And he got very close to 1 in 2. Okay. Karl Pearson, now he's a mathematician. He was clearly an academic because he had time to toss the coin for 24,000 times. And it get close to 1 in 2. John Carrick, another mathematician, he was actually in a concentration camp and he tossed the coin for 10,000 times and got close to 1 in 2. None of them got exactly 1 and 2, but so close as to say, yeah, it works. So although this is a very simple example, you can look at models and you can put them to test and you can say, well, yeah, they are actually representing what reality is. They are close to our expectation of what would happen. Now, problem with forensic science is we're only concerned with one specific event, one specific and unique event. You know, if I go to, if I put my hand down here and I place my fingers on there, if I go and do it again, is it going to be exactly the same? No, it's always going to vary. And of course, while we're dealing with latent print examiners and the bad guys breaking into houses or stealing cars or doing worse, you've got a particularly unique event. So all the probabilities we spoke about before, they've all been about series of events, something we can test time and time again. So is there any way we can talk about a probability of a single event? Okay. So if we consider rolling a dice again, go back to that example, okay? There's no physical state of affairs that relates to 1 in 6. It doesn't have any real meaning in the real world. You either get a 6 or you don't. It's as simple as that. So what can we do? Well, luckily, or again, unluckily, depending on your perspective, there is a way about thinking of a singular event. And it's this idea of it being conceived as a product of the mind. And I looked for an easier way to explain that, but it's not actually very easy to explain in simple language. Now, what that's called, or has been called by this guy O'Hagan, is subjective probability. And again, another one of those buzzwords you'll see bandied around about probability is objective against subjective. A warning for you here, subjective probability has a specific meaning, which I'll go on and explain. Okay. So subjective probability isn't just something that you thought up overnight. It isn't intuitive. Subjective probability is based on empirical observations. It's based on beliefs. Does any of this sound sort of vaguely familiar? I'm not sure if that was a yes or a no. But let's be very careful, and I need to stress this a lot. This word subjective does not mean that probabilities formed in this way, using this particular logical approach, are totally unfounded. They're not. They have to have some root basis. So we can think about what's the probability it's going to rain tomorrow. Okay. Clearly an example I can't use back in the UK because this is not one of those certainties. It's going to be 1. Oh, that was, yeah, I'll give over on the jokes now. Okay, so how might we arrive at that decision? How would we decide whether it's going to rain tomorrow? You're going out, you're going to go have a picnic or a barbecue, you're going to go to the beach. How are you going to decide whether it's going to rain tomorrow? Obviously in Florida this is a bit difficult because it rains the same time of day in Florida. So we'll have to put ourselves somewhere else. Okay. So we might think about what was it like today? What was the weather like yesterday? You know, what's the weather like been all week? What month is it? What season is it? What was it like last year, etc., etc., etc. Bits of information, empirical information, based on your experience and your knowledge and the fact you've lived in this area for a long period of time, that you will use to calculate the likelihood of that event. Okay. So for each of those, we can make a little statement in our head. We can say, well, if it rained yesterday, it always rains today. Or it always rains in April. You know, have these little statements going ahead, and they help inform and make that decision. Okay. And that's sort of fine. That works well for working out if it's going to rain tomorrow or if it's worth going to the beach or whatever. And that's great. But again, that's got some bit of limitations there in terms of forensic science. Because how do we get any consistency out of that? If I'd have asked you, you know, is it going to rain tomorrow? Would my expectation be you'd all go, yep, it's all going to rain tomorrow at exactly 4:39 p.m. It's just not likely. It's more likely that 50% of you are going to say it's going to rain and the other 50% is going to say sunny, and then you'd have a big argument about who was right and who was wrong. you know, that's just the way it is. So how do you get consistency? How do you get reproducibility? Well, a way of thinking of reproducibility is its consistency over time. So basically, if I make a decision last week that it was going to rain on Saturday and I make the decision this week, am I going to use the same information? And how am I going to demonstrate I use the same? You know, it's not really there. So what if we got really a little bit sort of OCD in a way and said, hey, let's assign numbers to this. Let's actually just think of some numbers. They can just be arbitrary numbers and say, right, I think the probability that it's going to rain tomorrow based on the fact that it's actually June is point whatever. Or the number that so-and-so is going to be this. And just assign numbers to it. And then if we all got together and agreed what those numbers were, then we would start get some consistency and reproducibility. Okay? Huge arguments about what the numbers are going to be. Yeah, but we would get that. And I'm not suggesting we do that before anyone starts worrying, but that would be a way of doing it. Another way we could do it, or a way we can extend that, is say we can think about competing propositions. So what does that mean? Well, proposition, just a posh word for hypothesis. So we can think about a particular event happening, and we can think, well, there is a likelihood that it will happen, and there's a likelihood that it won't. Propositions get a little bit more complicated because they're normally talking about something a bit more detailed than just is or isn't. Okay. If we do that, we can calculate what's called a likelihood ratio, which is a ratio of two probabilities. Okay. And again, this is a very simplistic way of looking at the definition of a likelihood ratio. If you read a book on probability, which I'm sure you're all going to do after this class, you will see that that's quite a big chapter on what a likelihood ratio is. But the beauty of a likelihood ratio is it's just a number. And we can use that number to express the weight, the likelihood of something happening. And it's a very balanced way of doing it. And why do we mention likelihood ratio? Because the software generates a likelihood ratio. The software you will use will give you a likelihood ratio. That's its output. Okay. So let's think about those propositions. And I'm sorry, it's a bit of a wordy and cluttered slide here, but we can think about two propositions. And again, you're probably going to relate this immediately back to fingerprints, which is fine, but you could think about any forensic science. So our first proposition is, what's the probability of the observations? Right, stop just there, the observations. What we're going to do is work out the probability of seeing what we've just seen, the observations we've made. I want to put it in a fingerprint context. What's the probability of my seeing 5 minutiae that match the latent print and the known? Okay, so think of it in terms of those terms. For the prosecution, we're going to say, well, what's the likelihood of my seeing that match of those 5 minutiae between the known and the latent print if the prosecution is correct and this really is the guy who did the dirty deed? This is the guy who did it. What's the likelihood of that? Now, again, we introduce some terms there. We're talking about this probability of observations. We're going to call that E, because I thought we would. And the hypothesis of prosecution, we're going to say this is H subscript P. So again, we're introducing a couple of those mathematical things, and you'll see why later. So that's going to be our prosecution hypothesis, our prosecution proposition. Now, the alternative proposition to that is obviously going to be the one by the defense. Okay? But it's not going to be just simply what's the likelihood of seeing it if he didn't do it. It has to be framed a little bit more complex than that. So we're going to say, what's the probability of seeing those observations, those 5 matching minutiae, if it really wasn't this suspect but another random individual? And that's just reflecting the fact that obviously if it's not that, if he didn't leave that particular latent, somebody did. It is a latent print. Okay? So you can see we've got those two competing propositions. So in mathematical terms, that's what it would look like. The likelihood ratio, and if you look at the top line there, the probability PR is the likelihood of those observations, the E, and that vertical line, which you'll see in stuff when this is written down, just means given. Like I say, you could have really just written given. So what's the probability of those observations given the fact the prosecution are correct and that individual really did leave that? And below the line, we're looking at the defense proposition, and we say, what's the probability of seeing those observations if the defense are correct and it was another random individual? Okay, So how does that work? Let's look at a very, very simple example. So remember we said that certainty is 1. So let's get close to certainty. And we'll say we have the probability of making those observations if the prosecution is correct. I've got the right suspect. It's definitely a match. If you want to put it in fingerprint terms, it's 0.9. So close to 1. Okay. And therefore, remember, they've got to sum up to 1 because they would be mutually exclusive events. It's got to be either him or somebody else. It can't be a third. There's no third option. So the probability that it was made by another random individual is going to be 0.1. Okay, everyone with me so far? It's tricky stuff, this, isn't it?
And you've made an identification? That's what you're saying?
No, I'm not saying we made an identification at this stage. I'm saying you were trying to work out what's the likelihood of that match. Okay, we'll deal with the identification bit a little later on. Okay, but at this stage we're just saying how likely is it? So I don't know if you've got a personal threshold. Yeah, I said 5. You know, if you want to drop it down to 3 or 2. It doesn't matter. Put it somewhere in your mind where you know you would not be happy to go just on the minutiae and the bifurcations, remember, just the bifurcations and ridge endings. I wouldn't be happy to call that. That's where we're talking about. Okay, that makes it easier to understand. So what's the likelihood ratio? Okay, well, P over D. Likelihood ratio is 9. Okay, well, what the hell does that mean? Simple way of thinking of it, and it is a simple way of thinking of it, it means it's 9 times more likely that that latent print came from that particular individual than from another random person. Okay? 9 times more likely. Is that strong evidence? 9 times more likely? Anybody think that's strong evidence? No? Anybody want to disagree and say, no, that's really good, strong evidence? Okay, hold that thought. We'll come back to it later. Now, with a likelihood ratio, one of the things really the only thing you need to remember for the next couple of days is that when it's greater than 1, then it supports the prosecution hypothesis. Now, I put it in very simple fingerprint terms. It's more likely to be the guy. Okay? So the bigger it gets, the more positive than 1. Okay? So let's assume we had a probability of making those particular observations, and it's 0.5. So now I'm saying, I've only got 3 minutiae between this latent print and this thing. It's like a 50-50 chance it's going to be this individual. Okay? You know, I don't know. Again, using those laws of probability, we know that the defense proposition has the same probability. It's going to be 0.5 as well. So you really don't know. This is, if you like, the ultimate inconclusive. I haven't a clue. So what would a likelihood ratio do? What would that tell me? So a likelihood ratio now is going to be 1. And the likelihood ratio 1 says it's no help at all. It says, well, yeah, it means nothing. That evidence is of no, because it's a 50-50 chance. And evidence that's valued at 50-50 is worthless because it's just as likely to happen as not happen. So, hey, you know, that's telling me nothing. Great. Okay. So what if we reverse it? What if we say, well, actually, it's more likely to see those observations from another random. You know, it doesn't really work with fingerprints, this. Not so easy. So you have to think of just another forensic science. It's more likely to make those observations from another random individual than it is from the particular suspect. That's the sort of observations you're seeing. Difficult to translate that into fingerprints because we don't tend to think that way. We tend to think in terms of the positive. And I'm not saying that's wrong, but that makes this example a little bit more complex. But we reverse it round, so now it's 0.8 for the defense. It's more likely the defense are correct. So what's our likelihood ratio now going to be? It's going to be 0.25. All you need to know about a likelihood ratio, when it drops below 1, becomes much less than 1, it's indicating the defense proposition is the most likely. Okay. Now, with probability software you'll use, you won't get a 1, and you will not get anything less than 1. The reason being is you're only going to use the probability software when you already think you have a match. You have to have something to match by definition. Now, if you want to put something in and not match it, when we play around with it tomorrow, it will give you a likelihood ratio less than 1. But the reality is, pretty much in the concept and the way we see this being used, you're never going to do that. So what we're interested in is that positive side of a likelihood ratio. Okay. So, just a reminder then, the greater the likelihood ratio, the more positive, the bigger it is than 1, the greater the support for the prosecution proposition. So clearly, if we're going to use this software in fingerprints, we want to see some big numbers, don't we? because that's going to tell us, yeah, that's really, really, really likely to be that individual. That's what we want, because we want to individualize as fingerprint examiners. Okay. 1 is no assistance, and less than 1 will support the defense. Okay. Now, likelihood ratios and numbers. Now, the trouble with numbers is some people understand numbers, lots of people do not understand numbers, and we'll look at some examples of that later on. But you can articulate likelihood ratios and probabilities in other ways. You can draw pretty graphs with pretty colors. You can have verbal scales. Okay? Each of those approaches has some benefits and has some issues. Do I know which is the best one? Well, not really. Ultimately, I know what works for me, but if we were ever to use and move forward to use this type of thing in a court of law, in our agencies to talk to detectives, we would need to find whatever worked for that group of individuals. So we can talk about it in different ways. We don't have to use the numbers. Okay. So here, we're going to introduce a verbal scale. Why a verbal scale? Because we think that a verbal scale is actually a little bit more approachable than the numbers. But I have to say, in previous classes, some people like the numbers better than the verbal scale. So that might not be true. So here's my verbal scale that I'm going to use. And it's not just sort of plucked out the air. It is based on research. It's taken from a number of these verbal scales that have been published quite widely in other areas of forensic science. And if you see on the left-hand side, we've got the likelihood ratio. Everyone familiar with this scientific notation? 10 to the 2, 10 to the 3. The number, the superscript number is basically the number of noughts. So 10 to the 2 is 100, 10 to the 3 is 1,000, 10 to the 5 is 10,000, all the way up to 10 to the 6, which is 1,000,000. Anybody sitting there thinking, hold on a minute, the likelihood ratio he calculated a little while ago was 9, but he's showing a verbal scale which, okay, 9 is on there, but he's going a verbal scale up to 1,000,000. So hopefully you're starting to think, when I talk about big likelihood ratio and the likelihood ratio we're going to see, they're likely to be a lot of 9s in there. Okay, what I've done is we've indicated what they are in terms of a verbal scale. So we talk about this limited, moderate, strong, very strong, extremely. Does either Sarah or I, do we actually know what a strong match of a fingerprint is? Nope. No and yes. You all know what that is. Because when you're actually doing a comparison and you get that particular latent print and you're looking at it and you're going, hey, Joe, can you come and look at this? Because it's sort of not, yeah, we've all done that. Or am I the only one? Yeah? Well, that's because at that point in time, you're sort of thinking, well, there's a strong likelihood that this is going to go, but I haven't got that telling extra bit that pushes it up one way or the other. I need to work at this bit more. So we do have an idea of what strong, very strong, limited means. Limited would be the opposite. You look at it and you go, nah. Okay. So we do have some idea of that, but we don't have a very precise idea. So if, again, in the future this ever used, would this be the scale that was being used? I don't know. And in fact, nobody really knows. Okay, so let's look at those numbers again. Remember, I've got much bigger numbers than 9. Well, how did I get those? Or how can I explain those? Okay. Well, remember I said in that first example I used 0.9 as being close to 1. Well, luckily, nobody pulled me up on that. Of course, that's not as close to 1 as I can get, because 0.9999999 is recurring is as close to 1 as I can get. I've stopped. I think I've got 8 there. And I've stopped at 8 because my calculator stops at 8. But I could have gone on with all the 9s and all the 9s. So this time I'm going to say the likelihood of seeing that 5 minutiae match is so likely, that the likelihood of it not is, the likelihood of it not is really, really small, 0.00001. Because remember, those have got to add up to 1. Okay, so what's my likelihood ratio going to be now? Okay, 10 to the 7. So that's 10 million. So it's now 10 million times more likely that it came from that individual than another random person. Is that strong evidence? Yeah, like big numbers, huh? Okay. So you can see where those numbers are coming from. Think back to the scale, and that was extremely strong evidence. Okay, so that scale is sort of working. It's sort of pointing in the right direction for what I want to see happen. Okay. Okay, this is great, but we're all latent print examiners. We've already stressed, and I'll stress again now, there's nothing particularly broken in fingerprints. I think fingerprints works well. We all know it works well. We know it's reliable, and so on and so forth. So why do we want to go down introducing likelihood ratios? What possible benefit can this have for this? Well, one thing about likelihood ratios is they're versatile and simple measure. They're a way of expressing the weight of evidence of a particular thing. Okay. And also they can be combined. And we're not going to delve into this too much at this particular point in time, but certainly back in Europe, all the DNA evidence is expressed as a likelihood ratio. You could combine a likelihood ratio from DNA with a likelihood ratio from a fingerprint match, with a likelihood ratio from a tire, with a likelihood, etc., and actually have a very formalized way of summing up what all that evidence meant. Okay? So I know it sounds a little bit like apples and oranges equals bananas, but it can be done. We're not going to do that. No one's suggesting we're doing that. That's for the future. But all of this comes out of what's something called Bayes' theorem, which is not a very particular thing that is well accepted in the United States, particularly in the courts. But this is another one of those terms you'll hear Bayes. You'll hear it built around. And Bayes' theorem is really a logical framework. There's hardly any maths in it at all, to be honest. It's a logical framework for interpreting a set of events. And what it says is this: the posterior odds, so the likelihood, remember we're using odds and likelihood, the likelihood of an event C happening is equal to the likelihood ratio, that's what we just calculated, remember, look in those two propositions, multiplied by the prior odds, one I knew already. Okay. Bit of a mouthful, much easier to explain and understand is what you want to know is what you can calculate times what you already know. Okay. And that's all Bayes' theorem is. It's just this framework for saying, if I know a piece of information beforehand, I can modify it with the information from my evidence to work out what the likelihood of an event taking place. And you can see there that anyone's done any courses on bias and such like, that there you've got that situation where you're actually using what's prior knowledge is there and modifying that prior knowledge rather than saying, I didn't know anything about it before and I'll work totally in the abstract. So it's very valuable in forensic science. So in the next sessions, what we're going to do is we're going to take those ideas a bit further forward and we're going to look how we can apply those to fingerprint examination.